Yeah. At the outset, let me thank the Honorable Dr. T.J. Sawant Sahib for giving me this honor.
इन्होंने शेयर किया है सर.
Am I audible?
Yes, sir.
To talk in front of the August gathering in a short-term training program on nanotechnology and science and technology. If you see the list of the
Sir, sorry
topics,
to interrupt, sir. Sir, sorry to interrupt you, sir.
Mhm.
But the another screen is visible, sir. I would request you to once again share your screen.
Okay. Can you see
Yes, sir.
now? Is it okay?
Yes, sir. Now it is visible.
Okay. So if you see the list of the topics in the short-term training program, the most of the topics are concentrated, centered around technology of the nanotechnology. So I would talk on bit science about the nanotechnology. So as I said, I should take this opportunity to thank Honorable Dr. T.J. Sawant Sahib, convener, principal or director R.K. Jain sir. I should not forget to mention Devasthali sir. Then coordinator, very important person, Kandalkar sir, Yadav madam, and other organizing committee members for giving me this opportunity to talk on the topic of my interest. The topic on which I am going to talk is ESCA or XPS. Before going to talk on this topic, let me introduce my institute. I come from very biodiversity rich and so far as water resources are concerned, self-reliant, a beautiful campus of Shahu University, Kolhapur, and I always feel proud to represent my institute. I am working as a professor in Department of Physics and working as a head of UC and CFC departments of Shivaji University, Kolhapur. Uh, this electron spectroscopy for chemical analysis, ESCA, or X-ray photoelectron spectroscopy, XPS. Why these are two different names for the topic? Basically, this is characterization technique, chemical characterization techniques for characterizing the nanomaterials. Here, X-ray photons are used to eject the electrons, to produce the electrons, and these electrons they are produced due to illumination of a photon. Therefore, these are called as photoelectrons. In these generated photoelectrons, they are analyzed spectroscopically. And keep in mind, these generated photoelectrons, they carry the signature of the material from which they get emitted. And therefore, electron spectroscopy method for analysis, chemical analysis of the material is the name, first name is ESCA. And for this we use X-ray. And therefore, X-ray photoelectron spectroscopy is the another name for the topic which I have chosen. Of course, there are other topics on which I can talk. I can talk on nanotechnology. I can talk on the technology. But I thought in this pandemic, there are many webinar lectures. I also have talked upon on various topics. And if you see the common audience, I thought I should talk on bit different topic related to the same field. And you can find my other lectures, maybe more than 6, 7 lectures on my YouTube channel. If you go and share and you can like the channel, you can see other lectures also. And tomorrow I'm going to put this lecture also on YouTube. Therefore, I thought I should talk on a bit different topic. It will add to the dimensions to your short-term training program. Therefore, I requested Dr. Kandalkar to choose the topic of my interest. So, thank you very much, Dr. Kandalkar. This is the list of the analytical techniques employed in thin film science and technology. Keep in mind, this X-ray photoelectron spectroscopy is employed in thin film technology also, where when we prepare a material, this material is being treated by the kind of electron beam or ion beam or photon beam. So depending on the energy of the electron, ion or photon beam, the interaction between electron, ion and photon with the material of the thin film, we get a secondary signal. And that signal can be in terms of electron, X-rays or photons, ions or some other form of signal. So depending on what we use to illuminate and what we get as a secondary signal, the techniques are divided. And not only that, depending on the energy carried by the primary beam. For example, electron having energy between 20 to 200 electron volt. The secondary signal, if it is electron, then it is called as lead. Then up to 30 keV, SM. Then 1 to 30 EDA. Then 500 electron volt to 10 keV, Electron Spectroscopy. Then more than 100 transmission electron spectroscopy, we have scanning transmission electron microscopy, electron energy loss spectroscopy. If we use ion, then various techniques are there. If we use photons, particularly X-rays and light, then XRD, XRF, ESCA and other techniques are there. So all these techniques, they are used to characterize the material, thin film material. If the thickness of a material is, if it is less than 1 micrometer, we call it as a thin film. So in this lecture, I am going to cover the use of a primary beam of a photon, that is X-ray, having energy greater than 1 mega electron volt, and the secondary signal is electron, and that technique is called as X-ray photoelectron spectroscopy, and this is used for chemical composition analysis. So we use this XPS technique for qualitative and quantitative analysis of the material or compounds which are present in the material. So far as chemical characterization techniques are concerned, there are few to list. EDAX connected to electron micrographs, SEM or TEM, electron spectroscopy, X-ray photoelectron spectroscopy, RBS, SIMS. So depending on their advantages and disadvantages, the range of elements which they detect, it is restricted. So for example, EDAX is restricted to the range sodium to uranium. Sodium to uranium. You cannot detect the elements up to Ne from hydrogen. And it has got its own limitations. With the help of electron spectroscopy, XPS, RPS, we can detect the elements from lithium to uranium in the periodic table. But if you want to cover whole range of the periodic table, not whole up to uranium, hydrogen to uranium, you need to go to SIMS. Somebody will ask, why not to go, or why it is not possible to analyze, chemically characterize the elements after uranium. We know uranium itself is a radioactive material, and all the elements after uranium, they are not chemically stable. They forms always isotopes, and therefore it is very difficult to find them in their parent nuclei form, and therefore you have limit up to uranium. With the help of XPS, we can analyze the elements between lithium to uranium, and detection limit is of course 0.1 atomic percent, and lateral resolution is 100 micrometer, and you can go up to 15 angstrom so far as depth of the material is concerned. Let us see the history of the X-ray photoelectron spectroscopy. It started in 1887 when Hertz he reported the photoelectric effect. When we illuminate a material with the photon, then electrons are emitted. So this is the photoelectric effect we know. Then Ronton He discovered the unknown radiations on the photographic plate. He called that as X-rays. And I'm telling the historical perspective and the research related to inventions related to my topic. In 1897, Thomson, he identified the electron as a charged particle. It has got negative charge, and therefore, in 1907, first XPS spectra was invented, or it was first observed. So they used X-ray photons for photo emission of electron and further analysis of these electrons. In 1954, maybe 50 years later, Bam, he first developed the XPS machine for for recording the XPS spectra. And he later, the same scientist who got later Nobel Prize in 1981, he developed method for recording the X-ray XPS spectra. In 1969, first commercial XPS machine came into market, and for his research, fundamental research on X-ray photoelectron spectroscopy, Bam, he received Nobel Prize in Physics, prestigious, the topmost award in the physics, Nobel Prize in Physics in 1981. So what information we get from X-ray photoelectron spectroscopy? I have shown few colorful diagrams on the slides. With the help of this very complicated and very difficult and very hazy diagrams, you can really identify what element is present in your material. You can calculate the surface composition. You can find the local chemical environment around this particular element. You can find out oxidation state of the material. You can find out valence band electronic structure of the material. So this is survey scan X-ray photoelectron spectroscopy or spectra, XPS spectra, and these are a narrow scan XPS spectra. With the help of survey scan, you can do qualitative analysis, and with the help of the narrow scan, you can do quantitative analysis. You can find local chemical environment, you can find oxidation state, you can find valence band structure, electronic structure of the material. So, photoelectron spectroscopy is the kind of a photoionization method, and then energy dispersive analysis type of method. So when we take an atom in the ground state, neutral atom, then all electrons, they are rotating around their respective orbits, and we say that a atom is neutral and chemically stable. But somehow, if you take out one of the electrons from the neutral atom, then this atom becomes deficient by one electron. And we say that the charge on the atom is +1, and this atom has converted into ion. And this is called as singly ionized atom. Singly ionized atom or ion. When atom gets converted into ion, the electron has to remove. So when this electron is somehow removed, then if you try to measure the energy of this removed electron, then it is the principle of photoelectron spectroscopy. So we illuminate a material with the help of a photon, maybe with the help of visible light, or with the help of ultraviolet light, or with the help of X-ray. Then there is an emission of electron, and we measure, we analyze these emitted electrons. These are called as photoelectrons. Then it gives you very important information about the material. You can have qualitative and quantitative analysis. So depending on what wavelength you use, what radiation you choose, the photoelectron spectroscopy is further divided into ultraviolet photoelectron spectroscopy and X-ray photoelectron spectroscopy. Keep in mind that the energy of a visible radiation is sufficiently low. It is not enough, sufficient enough to remove the electrons from the material, but the UV energy is sufficient and we can have bigger amount of electrons which can be emitted, and with the help of this UV radiation we can analyze the valence levels of the material, and the energy of the UV, it is between 10 to 45 electron volt, and this spectroscopy is called as ultraviolet photoelectron spectroscopy. Now if you want to examine the core levels, the deeper lying levels, 1s level, 2s level example, for example, then you need to use soft X-rays, X-rays having energy 200 to 2K eV for generation of the photoelectrons and further analysis of this electron. So I'm not going to talk upon UPS, but going to talk upon XPS. What is the depth and why it is called as a surface analysis technique? XPS is called as surface analysis technique. When we illuminate a material with the help of high energy radiation X-rays, for example, then the X-ray, they can penetrate a material, they can go far bulk in the bulk of the material, and there photoelectrons are generated. But unfortunately, the energy of this photoelectron is not sufficient to come on the surface, come or leave the material so that we can analyze that electron. So the only electrons which are generated within 10 nanometer depth, they have got sufficient energy to escape the material, and these escaped electrons, they can be analyzed with the help of this technique. Therefore this is surface analytical technique. Therefore penetration depth of this technique is around 10 nanometer. Immediately the point comes in our mind, the material surface, if it is 10 nanometer, within this 10 nanometer we have impurities or some foreign layers, absorbents, adsorbed materials. Yes, we should be very much careful that our material surface should be so clean that there should not be any foreign impurity level or layer on the surface. Even there should not be oxidation layer. That is because this technique itself is very much sensitive to your material thickness, and therefore this is called as surface analysis technique. This is a very simple phenomena if you consider the cell model of the atom. We know when we talk of vector atom model, when we talk of wave mechanical model of the atom, how we rely, how we believe on the cell model. But keep in mind, there are evidences to believe in the cell model, and there are many, and this is one of them. XPS is one of the evidence, or what you can say, XPS technique itself is one of the evidence of relying on the cell model, believing in the cell model. So when we illuminate a material with the help of X-rays, the X-ray can, the energy of these X-ray or photons is such that it is of the order of minus 13.6 electron volt or so, or even greater than that. So if when we have the photoelectrons, X-rays, having energy sufficiently high, then that energy is so high that those radiation, they knock out the innermost electron, the 1s electron. Certainly, obviously, the electron from 2s, 2p and other orbits also can be ejected. This is the one of the representative example, more probable example I have considered. So when these photons, they illuminate or they are illuminated on a material, atom of the material, then the innermost electron, they are knocked out, leaving behind singly ionized atom. And therefore, this atom is chemically unstable because there is a vacancy in the innermost core cell level, and which is not permitted. And therefore, this vacancy is filled by 2s, 2p or some other electron. Still, atom is singly ionized. and therefore this vacancy is filled by other electron. So according to Bohr's postulate, we know E2 minus E1 is equal to h nu. The photon or the radiation should be emitted. But many times these are non-radiative transitions. I can request organizers, if my connection somehow, if it halts, because here I can see the signal, my internet connection is not proper, they can halt me at any time and they can tell me whether my video or audio and video, whether it is continuous or not. So organizers, please be informed to me. Now, is it okay? Kandalkar sir?
Yes, sir. Yes, sir. It's okay.
Okay.
Go ahead.
So, if these radiations, they are non-radiative transitions, then energy is still there. Because in every physical phenomena, law of conservation of energy, law of conservation of momentum should be satisfied. If the radiations are not there, then the energy, where it will go? That energy is sufficient to remove the electrons in the outermost orbit. Because if you see this energy E2 minus E1, that energy is energy of this electron or maybe other electron. So the other electron is now removed. So you see, two electrons are removed, this one and that one. These are called as Auger electrons or Auger electrons. So in this process of illumination of a material by the X-ray, the atom becomes doubly ionized, and in this process two types of electrons are emitted. But these electrons, they carry the energy, or they are emitted with the energy, which is a signature of this ferrant element. And this phenomena or this aspect is used in analysis of the XPS spectrum. So let us talk about the principle of photoelectron spectroscopy. So as I said, it is a photon in and electron out process. The photon is absorbed. The atom initially singly ionized, then doubly ionized. When it is singly ionized, the innermost electron is knocked out. Let us suppose that initially atom, when it is in neutral state, it is illuminated by a radiation having energy h nu. It gets converted into singly ionized atom or ion A plus when one electron is knocked out. Now if you write for this reaction the energy reaction, or for this equation if you write the energy equation, law of conservation of energy requires that energy of atom plus photon energy should be equal to energy of ion plus electron energy. But the electron energy, what kind of energy electron would carry? Electron, if it is moving, if it leaves the surface of the material, then the only energy that is being carried by the electron is the kinetic energy. So electron energy would be kinetic energy. So let me write it as this equation to be equation for the kinetic energy of the electron, and that can be kinetic energy is equal to Ea minus Ea plus plus photon, or photon, let me rearrange this equation. For kinetic energy is equal to h nu minus the binding energy, because the energy difference between energy of ion and atom is the binding energy. That much energy is needed to take out the electron from the atom, and therefore that is the binding energy. So we have a simple relation: kinetic energy is equal to photon energy of the incoming X-rays minus binding energy. Now this binding energy is the characteristic of the material. So photon energy can be changed. Kinetic energy will depend on the photon energy. So but binding energy will remain as it is. So in the X-ray photoelectron spectroscopy, we have a graph of binding energy, or on the y-axis it is intensity versus binding energy, or intensity versus kinetic energy. So the intensity versus binding energy is the main graph. The kinetic energy graph changes because what radiation you have used, that will decide the kinetic energy. But you see, we carry out this experiment in a kind of machine called as a spectrometer. spectrophotometer or spectrometer. Spectrometer is a machine which records intensity with respect to energy or wavelength or wave number. So the electron has to leave this spectrometer also. Electron has lived our atom, but still it is in the avenue of this machine. So it has to cross the work function is the amount of energy required to take the electron from Fermi energy to vacuum level. So it has to cross the work function of the spectrometer also. So you need to add the work function of the spectrometer as well. So kinetic energy is equal to h2 minus binding energy minus spectrometer work function. Now, if you have the radiation, monochromatic radiation, X-rays having known energy, if you know spectrophotometer work function, and if you measure the kinetic energy of the electron which are emitted, then it is possible for you to measure the binding energy of that electron. And measuring binding energy of the electron means measuring binding energy of one particular element or electron from one particular element, means identifying what element is present, right? So you have to measure the kinetic energy. Now if you measure the number of electrons falling per unit area per unit time of that energy, that will be the intensity, and that will give you the chemical composition. So you can have both kind of analysis, qualitative and quantitative, with the help of XPS. So basic component of XPS instrument, they are X-ray beam, then sample, energy filter, this is the heart of the instrument, and detector. Either you can have energy spectrum, you can have spatial image, you can do the mapping, and you can have the depth profile also. You can go below and you can tell at one layer what is composition, at other layer what is composition, and third layer, etc., etc. So you can have energy distribution, spatial distribution, and the distribution up to 10 nanometer, keep in mind, across the sample. So what must be the components of the ESCA or XPS spectrometer? It would be, of course, sample, its holder, and the stage for insertion of the sample. X-ray source is must. Ion source for removing or cleaning the surface of the sample, or removing layer by layer for doing depth analysis, you need ion source. And very important is the energy analyzer. This is cylindrical mirror analyzer, electron analyzer, and the detector. And of course you need vacuum. I'm going to tell you why you need vacuum in XPS. Yeah, this is the point. Prerequisite of the X-ray photoelectron spectroscopy. We know here the photoelectrons are generated. Their energy need not to be modified because it is a kinetic energy. So electrons which are emitted, they should keep their energy. They should not lose their energy in the elastic scattering. That the electron should not collide with something. That's what. But if there is no vacuum, we know at room temperature we have large number of gas molecules which are present in the air, gas molecules, is it not? And there is a possibility of collision of these electrons with these molecules. So what is alternate? Remove those molecules. And how to do that? Create a vacuum. How much vacuum we need to create? We need to create, of course I have in my other lectures, I have calculations where we can relate the mean free path with the pressure. Mean free path is inversely proportional to pressure. So if you decrease pressure, the mean free path will increase. What after all is the mean free path? Mean free path is the distance, average distance between two successive collisions of the electron. Now, if this much is the size of your instrument, then mean free path should be greater than that. For example, here minimum path length is say 10 centimeter or maybe 50 centimeter or so. So correspondingly, you need 10 to the power of minus 5 torr pressure. So it is suggested that in XPS, you keep the very high vacuum 10 to the power minus 6 torr. Correspondingly, you can interchange yourself in the atmosphere or millibar or psi or Pascal, etc. 10 to the power of minus 6 or even better than that is preferably needed in the XPS. What should be the X-ray source? As I said, the X-ray should be monochromatic, and the X-ray, if its energy it is so high, it should be characteristic X-ray. And let me spare some time because I have got 1.5 hours to explain the process of science behind generation of X-rays. We know when high energy electrons they are suddenly stopped by a target, then we know according to law of electrodynamics, any deaccelerated charged particle it emits the radiation. Now depending on the energy of the deaccelerated electron, we have, and the energy of these radiations is in the range of X-rays. So bremsstrahlung or the white X-rays are produced. If the energy of these electrons is sufficiently high, then they remove innermost electrons, as just now I explained behind in the basic principle of XPS. So here in production of X-ray also same happens. So if it removes the innermost electron, then that vacancy is filled by outer electrons, and that energy is the energy of the X-rays. So if you see the X-ray spectrum, we have, depending on the bias voltage, we have the characteristic X-ray spectrum embedded in the continuous spectrum. So we need to use filters, and these are energy filters. You can use the crystal oscillator, or you can use the crystal having what you can say single D, so that 2D sin theta is equal to n lambda. At one particular theta you get the radiation having one particular wavelength, or you can use filters, many things you can do. So monochromatic radiation is needed. So what are possible sources for the X-ray sources? We need to consider the two facts. One is energy of this radiation should be high, and the energy spread. You need to keep in mind that though we call it as a characteristic X-ray, the characteristic X-ray doesn't carry a single wavelength. It is a energy spread. So if you look at various possibilities of the targets, you see there are other targets where energy is high, but their energy spread also is high. We should have less energy spread and high energy. And this criteria is fulfilled by Mg and Al. And therefore, frequently or generally, universally, Mgk alpha and Alk alpha radiations are used. This K alpha also has got two components, K alpha 1 and K alpha 2. I don't go in the details of K alpha 1 and K alpha 2 because you are science graduate, MSc in physics. Therefore, you must be knowing the difference between K alpha 1 and K alpha 2. So, Mg and Al are the targets. Energy analyzers. This is the heart of the instrument. Fine, you illuminate a material with the help of X-rays and the photoelectrons are generated. And these generated photoelectrons, whether they carry the same energy, kinetic energy, all electrons, whether they carry same kinetic energy. And if they carry same energy, what is the number of electrons falling per unit area, per unit time on a detector having same energy? So this needs to be analyzed. This should be smartly done. And this is done with the help of energy analyzer. And this is the heart of the technology of XPS. So what we can do, you can use the two analyzers, of course, in literature and in other books, they have given three type of analyzer. Hemispherical analyzer is there, concentric hemispherical analyzer is there, the cylindrical mirror analyzer is there. In the cylindrical mirror analyzer, the electrons, they are allowed to fall in the two mirror cylinders which are coated from inside, or they are called as cylinder, other cylinder, or one cylinder inside other cylinder. The outer cylinder is given zero bias and inner cylinder is given relatively positive bias. So the electrons, when they are flowing towards detector, they will be repelled by the outer cylinder because it has 0 volt, and they will be attracted towards the inner cylinder. Now, depending on the slits, locations of the slits and the applied bias, the electrons having one particular energy can be allowed to fall on a detector. Of course, this is complicated technology, but choice is a voltage. So voltage is proportional to energy, you can say. So you apply bias to inner cylinder, particular bias, and collect those only electrons. Measure intensity, applied another bias, measure voltage, measure energy, and you have the graph. Concentric hemispherical analyzer is the another analyzer which is frequently used, extensively used in these energy analyzers of XPS. So here in this figure, I have taken it from internet, Wikipedia. The calculated trajectories for 5 different kinetic energies at 5 initial angle are shown. Initial angular speed dependent on the chosen slit and aperture width and worsen the energy resolution. So you have detectors at various positions 1, 2, 3, 4 and 5 for example. So you can say that your detectors are at 5 radius of this hemispherical analyzer. And you have given different voltages to different radii of these analyzers. So there is a relation between energy, voltage and resistance. So at that particular radius, you get the radiations having that energy. See, simple. So in this way, the electrons are filtered. This is the simple example of 5-channel uh, uh, analyzer. You have 100,000 channel analyzer. So cylindrical hemispherical analyzer also is frequently used in XPS. Before proceeding further, let us visit to few concepts of the atomic spectroscopy. Electron energy states in this XPS are denoted by the X-ray notations. So let me introduce the X-ray notation. This would be very primary to all of you, but I feel it is very important to tell you because when we have XPS spectra with us and we see the notations on the XPS spectra and we go to the literature and we search our notes of MSc and see what this 3p by 3p half is equal to 3p 3 by 2 is equal to. So when I say atom is singly ionized, one electron is knocked out, then we talk of the binding energy of that electron. When we talk of binding energy of that electron, we need to consider that that is the only electron rotating around the nucleus. And we should know what are the corresponding spin orbit coupling or the energy states on the vector atom model are. And how can be done? It can be done, it can be considered by the fact that only one electron is around rotating, and that is the valence electron, you can say. So we know that when electron is rotating around the nucleus, it is orbiting around the nucleus, and not only that, it is spinning around the axis passing through it. When we represent orbital motion of the electron by a vector and spin motion of the electron by another vector, then precisions of these two vectors in the vector space will give you resultant called as resultant mechanical angular momentum vector. This L, S and J star are the three vectors. They have corresponding quantum numbers. I should not tell you origin of a quantum numbers. Hydrogen problem gives you origin of quantum numbers. Quantum numbers are due to for quantization. What after all is the quantization? Quantization means only few amongst many. For example, there are the angle between L and S would be from 0 to 360. So out of all these angles, only few angles are allowed. And who decides this? Quantum numbers decide this. And these quantum numbers, they are further responsible for S star and L star and J star. So X-ray spectra are very similar to one electron alkali atomic spectra, where we have doublet spectra, 2s, 2p, 3s, 2, 2p, 2b, 2d, etc. etc. And generally, in the vector atom model, the energy state is represented by 2s plus 1 Lj, where L is the principal quantum number. It is designated as level symbol as S, P, D, and F, capital letter, and J is the resultant quantum number. S is the spin quantum number, and this factor gives you multiplicity, whether it is singlet, doublet, quartet, quintet, septet, etc. etc. So here we consider only doublet because only one electron, we assume that only one electron is there. So let us suppose that there is only one electron in 1s orbit. Correspondingly, if you see the quantum number for 1s, L is equal to 0, S is equal to half, J is equal to half. Correspondingly, the state is doublet S half according to this. And the Auger notation is K because it is a K shell. And X-ray notation is electron is from 1s orbit and J value is half, therefore 1s half. Similarly, 2s half, 2p half, 2p, 3 by 2, etc. 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 We should know the difference between 2p and 2s, or 2p 3 by 2 and 2p half, and how much is the distance between these two. That also we can calculate. We know 2p electron in the sodium is responsible for two states, 2p 3 by 2 and 2p half, and the energy difference between these two is calculated by finding this energy and that energy, taking difference. So we keep in mind these X-ray notations, and these X-ray notations, they are available stationary states of an atom, where this is the free electron vacuum level, and the levels below this brown color, they are bound electrons, and here energy increases. K shell energy is the highest, then L1, L2, L3, M1, M2, M3, M4, M5, M6, M7, etc. And here principal quantum number 1, 2, 3, 4. So if you keep in mind this figure, then you can easily locate the state and its corresponding energy. Can we calculate corresponding energy? Yes, we can. We can calculate with the help of Bohr energy formula. But their principal quantum number, azimuthal quantum number is not there. J is not there. We need to add it from the vector atom model, or what you can say, from the fine structure. And you can easily calculate the energy. And here is the list of the energy. Here I have plotted the binding energy of that particular electron which are residing in 2s orbit. If there is no spin orbit splitting, this 2p, there is a spin orbit splitting, then 2p half, 2p 3 by 2. 3s, 3p half, 3p 2, etc. 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 for all. And there are ready-made table, you need not do it by heart, do not remember. In the computer itself, you have energy levels and their values. But for sake of understanding, you need to do it manually for understanding it. So, when you illuminate a material with the help of X-ray and get photoelectron spectra, what kind of graph you get? You get a graph of intensity of the electron with respect to binding energy or kinetic energy. If it is binding energy, you see the binding energy of the innermost electron is higher than the outermost electron. Therefore, binding energy increases from right to left. And if you have the same representation, same graph for the kinetic energy, then the kinetic energy of the innermost electron according to equation, kinetic energy and binding energy equation. Kinetic energy list now here, and kinetic energy increases from left to right. And on the y-axis, what is there? It is the intensity. It is counts, particularly if you are using channels, then it gives you counts per second, does it not? Number of electrons falling per unit area per unit time of that energy. So counts per second with respect to energy graph. So XPS spectra is collected for the silicon wafer with the MgK alpha radiation. So you get a peaks. So peak means you have to look for the lookup table. For example, here you have energy peak at 600k electron volt, for example. Then you can think of 1s electron, maybe this electron, maybe this electron, or that much. Only these many possibilities you have. But keep in mind, we know silicon and we know its atomic structure. We know its possible energy states, and the possible energy states of the silicon, they are 2s, 2p, 2s, 2p, etc. Oxygen 2s, silicon 2. So it is why oxygen also is there, because surface oxide has formed. So the peak position or the peak in the XPS spectra in the survey scan, this is survey scan, will give you what elements are present in the material. So this is lookup table. You have, this is the wide scan or survey scan spectrum of dirty silicon. As I said, this is relatively good silicon, only silicon oxide layer is there, only few peaks, 1, 2, 3, 4, 5, 6, but dirty, many peaks, where we have impurities like nitrogen, carbon, silicon, corresponding peaks are there. You will see that the nature of the survey scan spectrum is like a step, one, as if we are going in the temple, step by step. Why step like nature is there? Keep in mind, 2s electron is on the topmost position. So, stepped background is due to inelastic process, extrinsic losses from deep in the bulk. So, 2s electron is innermost, and therefore they are on the higher binding energy side, and therefore their energy is relatively more, and therefore you get this tape-like pattern. So this can be supposed as a starting point. Survey scan spectrum can be considered as a starting point of the most XPS analysis, and this allows us to set up subsequent high resolution XPS spectrum. For example, if from this spectrum, if you want to analyze how much silicon is present here, how much carbon is present, you just enlarge this. Keep in mind, for scanning this much, you require more time. Somebody will say, let us just enlarge this. So rescanning also will get that much, will require that much time. I'm going to tell you why. So this is the high resolution spectrum, or it is also called as narrow scan spectrum of the silicon vapor. Here, I have showed the 3 peaks, 1, 2 and 3. Effectively, I can see 1, 2 and 3 peaks. But these peaks needs to be deconvoluted. And here lies the beauty of the peak fitting, profile fitting softwares. Of course, I have another lecture for peak fitting also. I talk this in the ritual analysis also. So you choose a proper peak fitting software, and you have the positions. Depending on positions, it will give you the position of silicon 2p or silicon 3p, or if the silicon, this is for elemental silicon. If the silicon is in matrix, oxide matrix, for example, SiO2, then peak will be here. If it is in other oxide matrix, Si2O3, peak will be here. So beautiful technique this is. So if you have elemental silicon, if you have silicon in the silicon oxide, if you have silicon in other silicon nitride, for example, the peak position changes. So this itself tells you the chemical environment. That this will tell you qualitatively silicon is present. Then from the area under curve, you will know how much silicon is present. And the peak positions and deconvolution will tell you whether silicon is in the elemental form or is it in the other matrix. Now, as I told, SiO2, SiO2, hydrated SiO2, only SiO2, SiO, silicon nitride, amandine, then elemental silicon, they have got their own peak positions. And this is chemical state lookup table will give you in the computer itself, in the software machine, this software comes and it will tell you which silicon is present in your material. Peak fitting is very important. We know the peaks, they don't have the uniform background. It is tilted like this, step like pattern, is it not? So background here is different than this. So there is a background difference. So you cannot choose a background function like this, neither this, but this. So these are called as Shirley or Taugal type of backgrounds. I don't want to go in the details of this very technicality of the peak fitting, but you need to choose correct background. Of course, your computer software does it for you. What happens if you don't have XPS facility? Then we send a sample to our mate in one of the laboratories where this facility is there, maybe overseas, and we send him and send me back the XPS spectrum of my sample. And we don't know what kind of software he has used for peak fitting, for what is the correction background he has used. So we need to understand all these things. So full width at half maxima will give you peak width. Chemical shift means peak positions, that also will matter in peak fitting. Peak shape function. Pseudo-Ugat is a generally used peak shape function. It is the combination of Lorentzian Gaussian means n Gaussian plus 1 minus n Lorentzian type of function. This is called a pseudo-Ugat function. We frequently use it in ritual refinement. So that peak shape function also is very important in peak fitting. Instrument design factor itself has got its own profile fitting, experimental setting, and after all sample properties. So peak shape depends on, as I said, instrument, experimental, and sample characteristics. We need to take into account. And this is the pseudo-Ugat, as I said, peak shape. This is Lorentzian. This is Gaussian. This Gaussian is the exponential function and Lorentzian is the algebraic function. So if you have permutation and combinations for adding these two type of functions, then you get a kind of function which is very useful in the X-ray diffraction, maybe in the XPS, in any other, wherever peaks are there, and if you want to fit these peaks. So this, as I said, this is the L x minus x naught plus 1 minus eta g. Lorentzian and Gaussian is the pseudo-Ugat function. This is the case study. Let me represent some of the study related to my work. We have carried out the X-ray photoelectron spectroscopy study of antimony doped tin oxide thin film prepared with the help of spray paralysis technique long back, maybe 10 years back or so, where we see that there is a carbon. In the survey scan, we always see carbon because this presence of a carbon is due to exposure of our sample to air before scanning, or carbon contamination is happen to be there, bound to happen there in XPS. Of course, there are ways to remove this, but here we have presented our original result. Therefore, carbon we have shown, oxygen is there, antimony also is there. So antimony, tin is there. Sorry, tin. Antimony is not seen in the survey scan, but you can tell the peak positions. From these peak positions, we can tell which elements are present. And we have FWHM, peak height, peak area, and you can from peak area you can find atomic percent, relative atomic percent. How much percentage of C is there? 33%. Very bad sample. Oxygen. And if you remove this, we see that this is in the form of SnO2. If you add these two, and this is SnO2 type of thing. So we go for, I have plotted this in the different software. This is the graph given by the machine where we used MG target. So if you see the electronic configuration of Sn, where atomic number is 50, 1s2 2s2 2p6 3s2 3p6 3d 10 4s2 4p6 4d 10 5s2 5p2. So these are valence electron 5s2 5p2. So this is 4 plus valency of the tin, right? But from where we got the peak? 3p, 3d, 4d. So we have 4d, we have 3d, and we have 3p. Always it is not necessary to get a peak from 1s electron only. So when your Z increases, the energy increases. Therefore, the possibility of getting 1s peak is less. When you are below 20, as far as Z is concerned, then you will get the peak due to 1s, 2s, 2p electrons. So this is wide scan, survey scan, and the elements which are present, they are shown Sn, Sn, O, Sn, C, Sn. Spin orbit coupling. We know electron which is rotating around the nucleus, it is spinning also. So when electron is in p orbit, then it is splitted into doublet p half and doublet p 3 by 2 components. Or when it is in d, doublet d 3 by 2 and doublet d 5 by 2 components. Or f doublet f 5 by 2, doublet f 7 by 2 components. Of course, S is equal to plus or minus half. What after all should be the area ratio? Area of a peak of half, p half and p 3 by 2. It should be 1 as to 2. It should be 1 as to 2. 1 as to 2. 2 as to 3. 3 as to 4. You can mathematically prove this. And certainly, we have tested in our case when we take narrow scan spectrum, then for oxygen we got 2 peg, for tin we have got 2 peaks. Of course, D5 line, here 1s line, for oxygen 1s line we got. For Sn, you see oxygen Z is less, therefore 1s line we got. Tin 50, we have not 1s line, it is doublet. And for antimony, we have got 2 lines, but here the area ratio is not up to the theoretically correct. So from the narrow scan, again you can recalculate the atomic percentage. So don't rely on the survey scan, you go to narrow scan and then calculate the percentage, atomic percentage. For example, how oxygen, from the lookup table oxygen, the 1s level 531. So 531. Here you can see from 531 maybe here 1s level and Z is equal to near oxygen, right? So from oxygen, for antimony same, for tin same. From the lookup table you can find out whether it is antimony or whether it is tin. As I said, what is the area ratio of these two peaks? For D, it should be 2:3. Means area under curve of D5 by 2 peak should be 1.5 times that of area under curve of the peak D3 by 2. So we have area under curve of d pi by 2 here and d 3 by 2 there, and the ratio is 1.5. You can see. So here our theory also is confirmed. Cell model is confirmed. This is splitting, spin or repeat coupling, and this energy difference you can actually calculate the energy difference between SN 3d 5 by 2 and 3d 3 by 2. The difference comes out to be 8.43. I have calculated it. My student has calculated it, and this is the proof of the theory. Chemical shift, as I said, exact binding energy of the electron depends not only upon the level from which photoelectron is occurring, but also upon formal oxidation state, the local chemical environment and physical environment. So here you can see the narrow scan spectrum of the titanium peak scanned for elemental titanium and titanium in TiO2. So here what we can see, the peak has shifted by enormous amount, and that will give you the formal oxidation state. If Ti is in 2 plus state, or maybe other anion or cation having different valencies, different valencies peak positions will be different. So this is very handy technique to tell you whether in which oxidation state your element is there. So it is possible to study, discriminate between different oxidation state in the XPS. For example, you can do the depth analysis of the material. If you have material having 10 nanometer thickness or even 100 nanometer thickness, what you can do, you take XPS spectrum of the top layer, remove that layer by some sputtering technique, ion sputtering technique. It is easy. Then take again XPS spectrum, analyze, remove layer, take XPS spectrum, analyze. So in this way, you have either destructive technique or non-destructive technique. And non-destructive technique means what? You can be within 10 angstrom only, and you can have the analysis from this layer or that layer or that layer or that layer or that layer, and this is non-destructive technique. So you see, in this layer one other spectrum, here other spectrum, there other spectrum, there other spectrum, and you get sum of the spectrum and you get this. So effective spectrum can be analyzed like this only also. So from effective spectrum, we are not able to tell which elements are there, but you need to do the depth profiling in ESCA. And these are some of the results. Of course, I am not expert in the analysis of the XPS spectrum, but here the quantified XPS sputter depth profile of SI, TIB, SI multilayered structure, this one. Here you can say BTIO. So TIB, SI, and last is the SI. So sputter cycle means you just remove, take out one by one layer and take the spectrum and do the analysis. I have come to the end of my presentation. What are the limitations of this ESCA technique? Quantitative accuracy depends on signal to noise ratio. If your signal is too weak, then noise will override the signal. It is very difficult to identify your material. But if the signal strength is more, then it is very difficult, very easy to do the analysis with the help of XPS technique. Peak intensity, accuracy of the relative sensitivity factor, correction of the energy depends on electron mean free path. This is very important. So vacuum is needed. Quantitative accuracy is around 90 to 95%. It is not up to 100%. Under routine work, it still decreases by 5%. Analysis time is too much high. For survey scan, you require 10 minutes. Means maximum 10 minutes. For again narrow scan, you need 10 minutes. For depth profile, you need 1 to 4 hours. So it is time consuming technique particularly. Detection limit is 0.1 to 1 atomic percent. Measured area is up to 200 micrometer. Sample size in the earlier equipment it was 1 by 1 centimeter, 3 by 3. Nowadays in the present system you can go up to 30 centimeter by 30 centimeter. What are advantages? It is non-destructive technique, surface sensitive, qualitative measurements can be easily done, chemical bonding information can be obtained. And disadvantage, of course, it is very much expensive. Recently in our common facility center at Shivaji University Kolhapur under RUSA, Rashtriya Uchchatar Shiksha Abhiyan program, we have procured one of the XPS machines. Earlier this facility was available at Pune or Bombay or other metropolitan cities, not in rural university like us. Of course, our university has changing its space from rural to global due to such kind of programs and due to kind of research which is being carried out at Shivaji University Kolhapur. You must be and proud to say the fact that the speakers of this short-term training program, 60% of the speakers are from Shivaji University Kolhapur and they are product of this department. So the kind of research work which is being carried out at Shivaji University is getting enormous, what you can say, citations and those due to such kind of characterization facilities. In my common facility, in my means I am coordinator of this center, transmission electron microscope, XPS, bio AFM, micro Raman, XRD, and other techniques they are available. And the facility is ready to use, and soon this XPS technique also will be hosted in the. It has instrument has already come, but due to pandemic situation, we have few issues to be resolved, and those will be resolved within 1 or 2 months. Of course, high vacuum is required, slow processing. H and HE cannot be identified. You can go for other techniques. So I take this opportunity to thank organizers for giving me this opportunity. I had gotten a telephone call from Kandalkar sir, rather message I think. And sir, you have to talk because I've been the board of study member of physics since last 2 years. I'm board of study member of JSPM general science stream. Therefore, I cannot deny his request, and Devastali sir, Jain sir, Yadav madam, and Kandalkar sir's request was of paramount importance for me. Of course, I requested Kandalkar sir to reschedule my lecture due to my personal difficulty, but somehow it could not happen. And I thought I should talk on the topic on the scheduled time only. Only there was one rearrangement. Ajay's lecture was at my place and my lecture was now. So I hope those who have got questions, they might have typed in the chat box. I take